Let's count them down.
What do you want from me?
We want the numbers, Mason. The numbers are a broadcast. Lesson learned about the numbers there.
Alright, welcome back. In this video, I'm going to go over the love-making reaction, Diels-Alder. I made a grand total of $0 in the past 28 days. In 7 days, I'm about to be very happy. Because in 7 days, I become fully monetized on YouTube, getting passive income through ads. So I will no longer be saying I made a grand total of $0 in the past 28 days. I'll probably be saying I made 1 cent in the past 28 days. Something like that. It's gonna be a big day. But until then, you have something to focus on. Diels-Alder. Diels-Alder looks super complicated, but I promise you it is super easy. In fact, this is probably one of the easier reactions in organic chemistry. And I'm about to show you why. I know I said this about everything in every single video. Oh, this is super easy. This is super easy. It really is once you know the tips and tricks. And in this video, oh my god, we have so many tips and tricks to go over. So many. So, stick around. A Diels-Alder reaction, also known as a love-making reaction, because you'll see why, requires 2 things. A Diene and a Dienophile. A Diene is basically a carbon compound that has 2 double bonds. So you can see here we have a 4 carbon compound with 2 double bonds. A dienophile is what makes out with a diene. It loves dienes. A dienophile is basically a carbon that has double bond here, it's an alkene, with a functional group attached to it or another functional group attached. So 2 functional groups, 1 or 2 functional groups attached to it. So what that happens is these 2 things merge to form a 6 carbon ring with whatever functional group attached to it. So that's the only thing I want you to take away from this slide right here is a diene, which is 2 double bonds with carbons only, and a dienophile, which is basically a molecule that attacks diene, forms a 6 carbon ring. That's all I want you to take away so far. Now I'm going to teach you an easy method of doing this, an easy cheat code, and I call it the numbers method, because all you have to do is count to figure this reaction out. Honestly, it is so easy, you don't even need to write anything down. You can just do it in your head. It's that easy. Alright, let's talk about the diene first. The diene in a Diels-Alder, is always a 4 carbon molecule with 2 double bonds. So in every single Diels-Alder reaction you'll ever do in your lifetime, and I guess in organic chemistry too, it's going to look like this. This is always going to be your starting molecule. This does not change. This will never ever change. One very important component is this diene must be cis. As you can see, the double bonds are on the same side, right? So this is on the same side. It must be cis. Just don't worry about it. Honestly, just as long as the molecule looks like this, you're fine. If it looks anything else that's not this, you're not fine. It won't work. So yes, in every Diels-Alder reaction in OChem, the diene will always look the same. So every practice problem you do, every test problem you'll do, you'll always get the starting molecule. Now let's talk about the numbers. You won't understand what this is, but for now, I want you to number the diene from 1 to 4. So starting from top to bottom, name every single carbon from 1 to 4. So there's carbon 1, carbon 2, carbon 3, carbon 4. That's it. That's all you have to do so far. Now let's talk about the dienophile. This is different. The dienophile is the molecule that differs in Diels-Alder reactions. But one thing stays the same. You will always have a carbon-carbon alkene somewhere in the dienophile. Somewhere in that molecule, you'll always have an alkene. For example, here, we have an alkene here. For this dienophile, we have an alkene here. For this dienophile, we always have an alkene here. And we have an alkene here. These don't count, right? This is a carbon-oxygen double bond. That's not an alkene. An alkene must be from a carbon-carbon. So in every single dienophile, you will always see a carbon-carbon double bond somewhere in the molecule. So a little extra information is the more electron withdrawing groups on the Dienophile, the faster the reaction happens. Just in case you were asked a test question, the more carboxylic acids there are, the more CN groups there are, anything like that, the more groups there are present, the faster the reaction happens. I just put that just in case. But let's talk about the numbers now. So we numbered the DN from 1 to 4. Now what I want to do is number the Dienophile, only the alkene part of it, 5 and 6. So for example, this would be 5, this would be 6, this would be 5, this would be 6, this would be 5, this would be 6, this would be 5, this would be 6. Now notice we numbered the DN from 1 to 4 and the Dienophile to 5 to 6. 6 carbons, suspiciously enough, is our product. Right? So you'll see what happens. Where are you? Okay. Let's put cis and trans. Now this is probably one of the more important slides of this entire thing. On the Dienophile, you will encounter various molecules and functional groups. They will either be cis or trans. This is extremely important for the product, as you'll get the answer wrong if you identified it correctly. Okay, so let's back up for a second. The DN will always stay the same. It's the Dienophile that has the functional groups attached to it. So whatever groups it is, carboxylic acids, nitrogens, oxygens, whatever it is, it's always the Dienophile that has them. Now, when you encounter Dienophile and the functional groups attached, you must identify, is it cis or is it trans, if it applies. Here's how you do it. Let's look at this alkene here. Let's draw an invisible laser beam, and you will see the functional groups are on different sides of the laser beam. This means they are trans. For example, this one, if you draw an invisible laser beam going down the alkene, the functional groups are on the same side of the laser beam, so they are a cis. Let's do this one. So invisible laser beam going through the alkene, you'll notice they are trans. This functional group is on the top and this one's on the bottom, so they're on different sides. So that is trans. Here is the cheat code. If both groups are cis, so something like this, you will be putting the groups on dashes or wedges. Both of them will be on wedges or both of them will be dashes. You can choose. You will not be wrong if you put both of them on dashes or both of them on wedges. You get to choose if you want wedges or dashes. You have complete freedom, but you must make sure they are both on wedges or they are both on dashes if the functional groups are cis. If both groups are trans, you'll be putting one group on a wedge and the other one on a dash. It does not matter which one is on dash or which one is on a wedge. It just needs to be one of them needs to be on a wedge, one of them needs to be on a dash on the final molecule. If you do not understand this, then you'll get the problem wrong. You must correctly identify if it's cis or trans, and hopefully you understand that. Okay, let's talk about Meso and enantiomers. So here's another cheat sheet. So with Diels-Alder reactions, you will encounter meso compounds and enantiomers, unfortunately. This will occur if you have wedges or dashes, but this is not always the case, and I want to show you in a practice problem why this may not be the case. So here's a cheat code. If your Dienophile has cis functional groups, and the groups are indeed the same functional groups, you can have cis functional groups, but be different. So for this, I could put this as an ethyl group here and leave this as a methyl group, right? So methoxy and ethoxy, I can switch them up so they could be different, but they're still cis, right? They're still cis. The functional groups are still on the same size, but same side. But if I change this one to an ethyl group instead, right, then they're different. That's what I mean by that. So if the Dienophile is cis, but the groups are the same, you're going to have a meso compound. So you must state this in your answer if it asks. If your Dienophile is cis, but the functional groups are different, you're going to have enantiomers, and you need to draw them. And everything else. So if your Dienophile is trans and the groups are the same, enantiomers. You will have enantiomers, and you must draw them in your answer. If your dienophile is trans and the groups are different, it will be enantiomer. So the only one where it's meso is if your dienophile is cis and the groups are the same. So this is something I really want you to remember, especially for an exam. It will really help. And I'm pretty sure this works 99% of the time. I have not seen it where this is wrong. There always probably is that possibility, but I think it's too advanced for organic chemistry too. Okay, let's talk about the mechanism. Now, there is an easier way of doing this, but I must show you this method just in case your professors talk about it. I don't really like it. I think it's a little too complicated. I think you can do it so much easier, and there's a way, which I'm going to show you in the next slide, how to do it easier, but I'm just going to show you what the mechanism is and what's really happening here. So Diels-Alder is also called a 4+2 cycloaddition, because what happens is 4 pi electrons from the DN and 2 pi electrons from the dienophile turn into 6 pi electrons to form a 6-membered ring. Okay, so in other words, what happens here is we have a DN here, right, with 2 double bonds. Every double bond has 2 pi electrons in it. What's going to happen is this bond right here, this double bond right here is going to dissociate. It's actually going to form a bond between the DN and the dienophile. So it's going to form a bond here. The double bond on the dienophile is going to form a bond between the dienophile and the diene, and then this double bond will form here. So it's basically a bunch of pi bonds moving around. I personally do not like this method because look, it looks so complicated, right? Like, what is this? It looks like a coffin. You're gonna die doing this. Dienophile. Okay. Let's do the numbers method. Watch how easy this is. It's 3 steps, you're done. So remember how we numbered the DN or diene and dienophile? All you need to do is connect 1 and 5, so carbons 1 and 5, and connect 4 and 6. So literally the ends bond. So watch this. Watch this, watch this, watch this. All you need to do is do this. Ta-da! And we're done, right? So that's the first step. The second step is add a double bond to the left side, leftmost side, carbon-carbon. So here. So this is the most left side, right, of this entire hexagon, right? It's the most left here. You put a double bond there. That's it. Like, right? This, I literally did that, right? So look, this double bond moves to the most left side. That's exactly what we did. And we just made this bond here. That's what the line connection is here. Okay, step 3. Attach the groups on number 5 and number 6 if there are any. If they were cis, you will put them on wedges and dashes, either or. If they are trans, you put one on a dash and one on a wedge. Okay, so let's look at this, right? Here's our DN, here's our dienophile. The green lines here are the functional groups that are attached to the dienophile. This is cis because the functional groups are on the same side of the alkene. So we're going to put both of them on wedges. I could put both of them on dashes, it would not matter. But they must both be on the same thing. Like it needs to be either on both on wedges or both on dashes. I could have drawn this and put both of them, the X's on dashes. It would be the same thing. Okay? If they are trans, now look, you see this? If I do a laser beam right through the middle where the alkene is, one's on the right-hand side, one's on the left-hand side. There are trans. So we put the functional groups on number 5, and we put the functional group on number 6, and we put them one on a wedge, one on a dash because they are trans. They are opposite sides of the alkene. So we put one on a wedge, one on the dash. Plus enantiomer because we went over this, right? So we are trans, and it's going to be the same group. We have enantiomers. So you just got to draw the opposite one. That's it. So you understand what I mean? So once again, if you didn't understand this, this is 1, this is 2, this is 3, this is 4, right? We numbered the carbons. This is 5, and this is 6. The functional groups, if they're on the diene, right? If a dienophile, if there are functional groups, you bond it to number 5 and number 6. So let's number this again. 1, 2, 3, 4, 5, and 6, right? Number 1 and number 5 bond together like number step 1. So I said connect 1 and 5, connect 4 and 6. So that's exactly what we did. We bonded 1 and 5 and 4 and 6, and then we just attached the functional groups. Whatever's on 5 goes on 5, and whatever's on 6 goes on 6. And that's literally the answer. That's it. That's literally Diels-Alder. Now let's do some practice problems because you're ready. Alright, so what is the product of this? So let's do the numbering method first. 1, 2, 3, 4, because this is our Diene, however you want to say it. I don't care, whatever. And then we have our alkene here. So this is going to be 5, and this is going to be 6. This is our functional group here. You'll notice if you draw an invisible laser beam going down the alkene, they're on the same side. So we have a cis conformation here, configuration. So we can either put them on wedges or dashes. And look, all you have to do, watch this. All you need to do is you literally can just convert this into a wedge like this. Or a dash, it does not matter because they're cis. It needs to be the same. Actually, do this. Fill it in. Now, just all you just do is draw a ring and add this to carbon number 5 and carbon number 6. Like that. So once again, this would be carbon 1, carbon 2, carbon 3, carbon 4. This is going to be 5, and this is going to be 6. 1 and 5 join together, 4 and 6 join together. We draw a double bond on the most left-hand side carbon. Carbon. And in number 5, we just draw our little wedge and draw the rest of the functional group. Right, this is a methoxy group. I could have drawn OME, but this is the same thing. And for carbon number 6, we just draw in the group. We replace this. We replace this bond right here with a wedge or a dash. Does not matter. It just needs to be the same as number 6. And then just draw in the group. That's it. Just draw in the group. That's it. It's not too bad, right? Okay, let's do B. Here we have the diene. So let's number it. 1, 2, 3, 4. The dienophile, we have an alkene right here. So this is going to be 5 and 6. If it helps, you can rotate the molecule. So we have our alkene here. Double bond. The functional group is on top here, and we have a functional group on the bottom. So we have trans configuration. All right. So what do we do now? Well, we see that we have trans. So this means that this functional group here is going to be on a wedge, and this one's going to be on a dash. So all you have to do is replace the bond from the 5 to the actual, this part right here to a wedge, and you can replace this one to a dash. And that's it. So then draw our molecule, right? We have our ring. Every single practice problem is going to have a ring with a double bond here. And then all you have to do is on number 5 and number 6, draw our functional group. One's going to be on a wedge and one's going to be on a dash because we have trans. So just draw in what's there. Plus for enantiomer because we have a trans configuration here. Let's do C. The diene, 1, 2, 3, 4. Now for the dienophile, we have an alkyne. But don't worry, it's still the same thing. 5 and 6. Now, what's going to happen is, yes, we're going to have our 6-membered ring with the double bond forming between 2 and 3. But also, we're going to have a double bond between 5 and 6 because only one of these pi bonds forms the bond between number 4 and number 6. But the other one, the extra one that's there, is going to stay there. Now, notice that we have the same groups here, so we have no wedges or dashes involved. So all you have to do is just draw this on number 5 and draw this on number 6, and that's our answer. So here we have our ring, the normal double bond that's here, and we have another one here between 5 and 6, and our functional group there. Right, so this bond and this bond is this. Sorry, this and this. This is this, and we are a functional group. And that's it. That is Diels-Alder. If you found this video helpful, please like and subscribe. Until next time, later. An invisible laser beam, you'll see that this group is on top and this one's on bottom, so we have a trans issue. Not trans, that sounds bad. That is so bad. You have it's trans, okay? Oh boy, I want to get canceled. Put this as a wedge. It is like to be connected to this. And then this is a dash. That is so bad.